So we're live. So my YouTube officer, can you please check that everything is fine? So it comes with a little delay, but within a few seconds we're ready to get started.
Everything fine.
Everything fine. Okay. Simulation of a mechatronic machine, lecture number 7. Today is a day. Today, as I mentioned, 3 things will happen. First thing that will happen is that we're going to have a full lecture without technical difficulties. Who believes that? I don't know. That we will see. And then the second thing that will happen is that there is a in-class quiz where the success rate is 100%. Yes, 100%. And I'm gonna very soon I will put the first in-class quiz on. It will be related to augmented formulation, the method that is based on Lagrange multipliers. And I will repeat the answer before we entering the in-class quiz. Let me think, 3 times. I will repeat it 3 times, so listen to me. So whenever I mention something 3 times, you know that that next slide is something that I'm asking that very same subject matter. All right? Third thing that will happen today is that we will solve the somewhat complicated mechanical structure, planar mechanical structure. We will solve the dynamic response of that mechanical structure. And that's going to be close to miracle. So you will have a hard time to believe that by yourself. But all the knowledge we have gathered so far within these 6 weeks, so we will put everything together. And we will systematically model the 2 different structures, and then we're going to solve them by using a MATLAB. And then I will I will make an animation about their responses. And that's going to be something that I'm sure like after that you all want to have a good group hug with me. We can make it happen. That could be during the break or whatever you want. So those are the 3 things that are hoping to happen today. So lecture number 7. So lecture number 7 was not even in our original plan, but as I'm a little behind of the schedule, there is going to be today's lecture. This is the last lecture prior or before the midterm exam. I'm not going to have that many slides. New material is basically just summarizing what we have been discussing. I'm going to show you an example, actually 2 examples, how is that you can use augmented formulation. And then the major body of today's lecture will be related to recap, summary. And in the summary, I have a list of items that I'm expecting you to know when you get into the online exam. And then each one of the items are rated by number of stars. More stars, more important is the topic. So that's the summary. So you can have an overview about the matters that you have to master when you get into exam. And then a few words about how is an exam itself. And just shortly, it's going to be online exam. But how is that you can do the exam? I will get back to that a little later today. Okay, so augmented formulation, that's the first part of today's lecture. And what comes after that is summary. But now, before that, let's summarize what we discussed last week. And remember, the last week was the most painful week so far in your life. So what we discussed was very theoretical, very hard to get a grip, like what exactly is this concept of virtual work, and how is it you can apply that to inertial forces. And then even more complicated than that, we discussed about augmented method, augmented formulation that is based on Lagrange multipliers. And we concluded that it's a part of the optimization problem, and this is comes from the pure mathematics. Today we will get back to that. And I want to have a good physical interpretation of different components we need in an equation of motion. So that's going to be something very, very important because I will ask something related to that in exam. So what are the physical interpretation, for example, Lagrange multiplier? And based on today's lecture, you should be able to explain that to me. Okay, but last week we looked at the generalized inertial forces. And generalized inertial forces, as the title implies, are the forces that are expressed by using generalized coordinates. All right? And now if you look at how is a conventional way to express the inertial forces, it is a mass multiplied by acceleration. Because we're looking at the particle acceleration, and the particle acceleration can be expressed as it is shown here. So this is a particle acceleration, and the particle acceleration is expressed by using global coordinates. So r dot dot, which is an acceleration of the particle that consists of two parts or two components that are along the global x and the global y axis. Okay, that's not good because we want to express all the forces using generalized coordinates. And if we have one body, there will be a total of 3 generalized coordinates. Now, how we can make this trick, how we can make this mapping to happen? So we can make this mapping to happen with help of concept of virtual work. The concept of virtual work says that force multiplied by displacement, which is a virtual displacement, that is a virtual work. Now that's exactly what we're doing here. And it sounds like, okay, why? Why is that we do this? And the why, it is involved with this component, delta R component. By the way, let me switch the view for you guys. I guess that this is more clear. Isn't it not? Quite good. Okay. So everything is related to this component. So this component is the one that allows us to get the mapping between the global coordinates and generalized coordinates. And that's how you can make that happen. You can make it happen by using this equation. And in this equation we have delta R equal than delta Q. So here is the relation. This is what we are looking for. Now what is actually relating those two matters together are the mapping matrix, which is a partial R, partial Q. Partial R of any particular particles in the body that with respect to partial Q. And the Q is generalized coordinates. Now that's the concept behind, that's the big picture behind. And now what we then did, we substituted the description of acceleration to that equation, and we also described, or we actually substituted the mapping matrix as it is written here. So the mapping matrix is a matrix that consists of 2 rows and 3 columns. Rows are associated to global coordinates, columns are associated to generalized coordinates. Okay, so we substituted all that to description of generalized inertial forces, and it's a big mathematical mess. But that's all right, because we are allowed to use the symbolic math tools, and with help of symbolic math tools, we can finally express the generalized inertial forces as it is shown here. What is that we're going to have in this equation? There will be something called mass matrix, and the mass matrix will be linearly related to accelerations, and this is a acceleration of generalized coordinates. And then there's another component that will be quadratically related to velocities, and that's this component. So there is a mass and then quadratic velocity wave. Okay, that's what we studied last week. And the mass matrix in details looks like shown here. So it's a matrix that consists of 3 rows and 3 columns. 3 rows and 3 columns because each one of the rows and columns are associated to generalized coordinates, because that's how we wanted to express our inertial forces. Okay, how are these, how is the mass matrix? It consists of a submatrix that is located here in the upper, so let me go back here. So upper left corner of the mass matrix is a 2 by 2 matrix, which is a diagonal matrix. And when you look at the diagonal components, it's a mass of the body. Then lower right corner, we have a scalar component that is a mass moment of inertia. It's associated to generalized coordinates theta, rotation. And it tells how the mass, inertia, resists the rotational motion. And it depends where the body reference coordinate is located. And then we have one more component that couples the translation and location. This is a component that I don't have a clear physical interpretation. That component will be equal to 0 if the body reference coordinate system is located in the center of the mass. Okay, so that's how the mass matrix look like. And then we looked something that is quite difficult to understand. And my recommendation regarding this thing that is quite difficult to understand is that don't get confused about mathematical details. So we just simply need to look at the big picture here. Now let me explain you the big picture. We concluded that when you use a concept of virtual work in such the way that the virtual work is imposed to all the generalized coordinates when you have a constraint system, which is a multi-body system, because in the multi-body system we have the constraints, you cannot set this equation to be equal to 0. You cannot do that because you are not accounting the constraints. And generally speaking, there are two approaches to account the constraints. You can either substitute your constraint to this equation, so you can do the substitution procedure, and that's one way. We are not going to look at that today. And then there's an alternative where you're adding the constraints to your original equation. And the adding will be actually carried out with help of Lagrange multipliers. And that's exactly what we're going to discuss today. Okay, this equation basically says, external applied forces, which is F, is equal than mass multiplied by acceleration. That's what it is. But this only holds, it's only valid for unconstrained system. And in multi-body system, we always have the constraints. So what to do? Let's use the concept of augmented formulation. And in augmented formulation, we are adding a component to original equation. I'm going to flip back to this one here. So this is how the equation look. Hold on. So I will erase this. So this is my original equation. And now I'm going to add something to this equation. And what I'm adding is this guy here, which is a Jacobian matrix multiplied by Lagrange multipliers. What is this? Okay, in mathematics we learn, pure mathematics, we learn that Lagrange multipliers are the price you have to pay because of the constraints. Okay, what it means for us, people from mechanical engineering. So what are the constraints? Joints. Those are the joints. So what's the price? Reaction forces. Reaction force is due to the constraints. That's the price we have to pay. Okay, so where are the reaction forces here? They are actually Lagrange multipliers. Those are the reaction forces, and if you look at the magnitudes, numerical values of Lagrange multipliers, those are exactly the same than reaction forces. And when you look at the Jacobian matrix, this guy here, it tells where the forces are located in our system. So that's what it is. So Jacobian matrix multiplied by Lagrange multipliers is a reaction forces. The numerical values for reaction forces is a lambda, and we have equal number of lambdas in our system than the number of constraint equations. Okay, example. So we have here a pendulum. In a pendulum we have one beam-like body that is constrained to ground with help of revolute joint. How many constraints we have in this system? Okay, so we back in point 0, I guess, because I thought that we kind of like friends a little bit that direction, and we can have fun together with like communicating like this, but not anymore. So it's all gone. You don't know me any longer, or what is wrong? My shirt is different. Correct, yes, my shirt is different. So I should always wear the same shirt. That's what I'm telling to my wife. She don't believe me. Okay. Okay, we have a pendulum. We have one revolute joint. What's the number of constraint equations we need to describe the one revolute joint? 2. Okay. So what are these two? So two constraints. So these two constraints make sure that this point stays in this particular location no matter what. Okay. So what are the reaction forces then? Reaction forces are the ones that are associated to this revolute joint. So there's a force in these two directions. How large is this force? Those will be told by Lagrange multipliers. And in this case, if you make a list of Lagrange multipliers, there will be 2 Lagrange multipliers because there must be equal number of Lagrange multipliers and the constraint equations. Constraint equations are always somehow related. In our case, they are related to reaction forces. Okay, so now this is what we added. But now it's not enough, because unknowns in our system are, hold on, let me delete this. Unknowns in our systems are, well, the original unknowns, which is generalized coordinates. That's a question mark. That's what we are solving here. But because we added the constraints with help of Lagrange multipliers, we got additional set of unknowns. Additional set of unknowns is this, Lagrange multipliers. So this guy is an unknown, this guy is an unknown. So we're adding the number of unknowns. Now because of that, this equation alone is not enough to solve the system. So we need something else. Something else comes from the constraint equations. This is a system we can solve to find out the dynamic responses. Except we cannot, because this is a system that is called differential algebraic equations. And there is not good ways to solve this in forward of time. So the final step we wanted to do is that we want to convert set of differential algebraic equation to be ordinary differential equation. How is it we can make that happen? Well, we can take this constraint equation here, and we can differentiate that twice with respect to time. And once we do that, then we have this form here. That's what we are after. So that's the equation of motion, and that we can create for any mechanical system we want. Well, at least the ones we are studying, as an example, and many others can be. You can use this equation and apply the equation to solve the dynamic responses. Okay, here's the big picture. I have here mass matrix. You know what that is. That's a system mass matrix, and depends on the number of bodies. Then I have here Jacobian matrix, which you are already familiar with. That tells you can get the Jacobian matrix by first make a list of constraint equations, and then differentiate the constraint equations with respect to generalized coordinates. Then I have here Jacobian matrix with transpose operation. Okay, no surprises here. Zero matrix just to match the dimension. Then I have here vector of unknowns. Listen to me. This is a vector of unknowns. That's what we're going to solve. So what is it we solve? We're solving first the acceleration and Lagrange multipliers that are reaction forces. Okay, here we can integrate velocity of generalized coordinates with help of integration procedure. From here we can integrate position, and then we're done. And then we can increase the time, and we can redo the whole thing. That's what the dynamic solution, or integrating this in forward of time, that's what it is. Okay, let me emphasize the unknowns. Unknowns are Lagrange multipliers, this guy, and generalized coordinates. Unknowns are generalized coordinates and Lagrange multipliers. You got it? Unknowns in this case are this vector, which is generalized coordinates and Lagrange multipliers. Okay, clear. All right, then I have here vector of externally applied forces, quadratic velocity vector, which may be equal to 0 depending where you put your body reference coordinate system, and then the one that comes when you differentiate your generalized coordinates, your constraint equation twice with respect to time. Ready for in-class quiz? Yeah. Any guesses what is that I'm going to ask? In augmented formulation, unknowns are. Please be my friend. Okay, hold on. Okay, can you see it? Okay, it's there. So I have already 39 people that have locked the system. 51 already. Okay, if you're not sure, please communicate with your fellow student, please. Okay, so while you is this clear, or would you like to get a little more extra information regarding this problem? It's clear. Okay. Then we're gonna move on. Here it is. Here's my first example. I will get back to this in-class quiz and the solutions of the in-class quiz soon, but first I would like to explain my first example to you. So in my first example, I have a planar system, and this is, I must admit that there is a, the drawing is a little bit confusing. But what I would like to show here is that there is one moving body only, and the one moving body is this beam-like body, this one here. That's my moving body. The moving body is constrained to ground in two different locations. So it's constrained to ground in a point P that is located here, and it is constrained to ground with help of primitive joint. This primitive joint constrains the motion in global x direction, and this is a motion that is not possible. That's the motion that is constrained. So it's a primitive joint. Maybe better to change the color. So this is a red arrow showing that this is not allowed to go to that, to move that direction. Then there's another primitive joint that is located in a position Q, and the position Q is this one here, this position. And now this one here, the motion in a global y direction is constrained. So that's the constraint. So those are the two constraints. Okay, few questions. What's the number of degrees of freedom of this system? Okay, because yes, I know, because today, okay, let me, what is the way that we can communicate today? No way today. Okay, then let's vote. Okay, is it 0? Is it 1? Is it 2, 3, 100? You have to cast your vote. So who is saying that is 0? No one?
There is one development joint and one primitive joint. Yeah?
There is two primitive joints.
Two primitive joints. Okay.
You go for 1. 0. Excuse me, 0.
No.
0. 0? No one? Okay, who is taking 1? All of you. What the heck? Why is that you don't say this to me? So, okay. I remember, because of the shirt. I look so different, that's why. Okay. Okay, is 1. How is that you know that is 1? Because we have one moving body that comes with the 3 tenurized coordinates. 3 tenurized coordinates and 2 constraints. 3 minus 2. How many Lagrange multipliers we will have in the system? 2. Okay, now comes the difficult question. Now this is, you need to do serious math to answer this question. How many unknowns? Unknowns, and let me write that in a green font. Here are the options: 0, 1, 2, 5, 6. That's it. Who is voting for 0? That's good, because that would be no problem, because no unknowns. Who is saying 1? 1 degrees of freedom, 1 unknown. 1 degrees of freedom, 1 unknown. No one? 1 degrees of freedom, 1 unknown. No one. Okay. 2? No one. 5? 5. It's 5. Why is 5? Because we have 3 tenurized coordinates plus 2 Lagrange multipliers. We have 5 unknowns. So the system consists of 5 unknowns, and those are the ones we are solving here. Okay, let's solve the whole thing. So let's make it happen. So we're going to follow the certain steps, and once following the certain step, we can get the equation of motion automatically. The worst mistake you can do in a multi-body dynamics is thinking. Absolutely no thinking. Thinking is not allowed here. You're just following the certain steps. Always the certain steps. And always, 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 you must follow this equation. No shortcuts. Shortcut is a criminal action. Not allowed. You're just following the steps and you get out everything automatically. Okay, so let's follow the steps. Step number 1, mass matrix. All right, we could do it in a hard way as shown here, and the hard way is that we will use this volume integrals to define the components needed in a mass matrix. In the first component is a 2x2 matrix where there is a mass of the body. No need to do any volume integrals. It's simply a mass of the body. And then second one, which is a mass moment of inertia. So if I assume that this is a beam-like body, a thin body, I can assume that this body y direction is equal to 0. Then I can express it in such the way that I simply integrate u bar x power 2, and I'm going to integrate that in x direction. So that's basically the mathematical operation I need to carry out. But again, just use the mathematical tools. And once I do this computation, I will get mass power length, mass multiplied by length power 2 divided by 12. This is what we got last week too. So, and I'm going to get the diagonal representation of the mass matrix. Why is that? That's simply because if I look at this picture again, look where the body reference coordinate system is located. So based on this location, I could tell that the mass matrix will be diagonal mass matrix. Okay, step number 1, done. Step number 2, Jacobian matrix. Okay, what are the ingredients we need in Jacobian matrix? We need constraints, and we need generalized coordinates. Okay, so the constraints are associated to 2 points. Point P, which is here, and point Q, which is here. Okay, let's express these locations with help of this equation that we are quite much familiar with, and then once we have this equation, then we're ready to impose the constraints. Okay, clear? So the first, okay, let me see what is the first point. First point is P, the one that is located here. So this is a P point. First, we have to travel from the origin of the global coordinate system, the body reference coordinate system. That will be carried out by vector R. That consists of 2 components that are unknowns. I don't know what they are. Then I have to account the orientation of body reference coordinate system. Orientation is an unknown. I don't know what the angle theta is, but I will solve it. And then I'm going to use the vector u bar to travel from here to my final destination point P. Okay, so the vector u bar will be, when you look at closely, the x is pointing this direction, so I must travel minus L divided by 2 direction, x direction, and y direction is going to be 0. And then I'm ready to impose the constraint which will be associated to this component, because the motion in a global x direction is not allowed. That must be equal to 0 all the time. So here's my first constraint. You following me? Yes? Everyone? Okay, good. So we're on the same page. Okay, then we're going to follow on, and we're going to move on to point Q, this point. Exactly same business. But, now we're going to first move the body reference coordinate system. We're going to account the orientation. And now the vector u bar will be different because we're going to be in the other end of the beam-like body. Okay, vector u bar is going to be L divided by 2 because we have to travel the positive direction. The y will be equal to 0 as was in the previous case. And now we're ready to impose the constraint. This time the constraint will be associated to y direction. That's it. I got second constraint as shown here. Then I have the ingredients that I needed to compute the Jacobian matrix. So the list of generalized coordinates is Rx, Ry, and angle theta. And then just mechanical mathematics. I will take the constraint equation 1 at the time, and I will differentiate those with respect to generalized coordinates. That's going to give me Jacobian matrix. Jacobian matrix consists of 2 rows, 3 columns. Columns are associated to generalized coordinates. Rows are associated to constraints. Clear? Okay, step number 2, done. Checked. Vector of generalized external applied forces. Now, only force that is applying in a system is not, is a kind of in a small font. So is this one here is a gravity force. Gravity force is applying in the center of the body reference coordinate system, which is a very good news for us because it simplifies the expression of vector of external applied generalized forces. How is my force in global coordinate system? So it's going to be, x component is equal to 0. Y component will be mass multiplied by gravity constant minus direction. Okay? It's applying in a position that is expressed here. So it's applying in a position where the O here is in the center of the body reference coordinate system. So this guy here will have 0 components. So it's going to be vector with 0 components. Okay, so it simplifies my expression quite a bit. So my mapping matrix turned out to be the one that is shown here. So I'm basically taking this position and I'm differentiating that with respect to my generalized coordinates, and then I will get the mapping matrix. Mapping matrix multiplied by forces in global coordinates, that's going to be my generalized coordinates, generalized forces. And let me see, here it is. So here's the final solution. So it consists of 3 components: 0, mass multiplied by gravity constant minus direction, and 0. Okay, step number 3, done. Quadratic velocity vector. I'm not going to even compute that because I can see that from the mass matrix, that was a diagonal matrix, that this will be equal to 0. Step number 4, checked. So tick the box. Checked. Step number 5, QC, which is the one that I get when I differentiate the constraint twice with respect to time. This is a little painful component because this is the same that we look when we compute the kinematics. So we have first here Jacobian matrix that is multiplied by velocity of generalized coordinates. Here's my Jacobian matrix, here's my velocity. That will give me a vector of 2 components, this and this. Those components will be differentiated with respect to generalized coordinates, which gives me a matrix. And the matrix, where it is it? This is my matrix now, so I copy paste from the previous page quite a bit of material. So this is my matrix, and then this is finally then multiplied by velocity of generalized coordinates. No thinking. It sounds a little bit like cumbersome and difficult, but very straightforward. Okay. Step number 5, done. Step number 6, this. Constructing the system matrix. And what I have here, this is my system matrix. So I have here, when you look at this closely, I have here mass matrix of the system. So a system consists of one body, so it's just a one mass matrix. Then I have my Jacobian matrix here. Transpose of the Jacobian matrix is here. And all these will be inverted. That's fine because I have computers that can do the inverting for me. Then I have this 2 by 2 zero matrix here. Here's my externally applied forces plus quadratic velocity vector, which was equal to 0. And then the QC component is here. That's it. My unknowns are listed here. So it's the acceleration of generalized coordinates and Lagrange multipliers. Clear. So I'm solving not just the response, but the reaction forces too. Okay. Okay, let's make it happen. So, are you ready to solve this in MATLAB? You are. Okay. How is going to be the response then? Now, the thing is that I need to close this connection because, I need to put the VPN on. So we'll see how it's going to be. Oh, it is on. Oh, That's quite surprising. Let me see, where is my MATLAB? MATLAB, I thought that it's am I in the right location now? MATLAB 2 here. Okay, then I need to make a little bit of changes to my streaming setup. So I need to close, let me see, this and put this on. Oh, okay, that's not looking very good. I need to move it here. How it looks? It looks all right. Still all right.
Yeah.
Kind of all right. Let me make this a little bigger, and then I'm gonna lock it here. Okay, and then back to MATLAB. Okay. Can I open my MATLAB and can you check like how is the streaming? Is it still all right?
Yeah.
Okay, good. So I made a short MATLAB code where I'm simply expressing the equation of motion as it was written in that slide, and then I will solve the response. Okay. Okay. So here it is. So I have few variables. So I have here time, and then the vector that tells how are my positions of velocity. So I have x dot, y dot, theta dot. So those are the generalized coordinates and their velocities. And then then a little bit about how is my description of my integration. And if I look at this, is the one that where the most of the material I can find in this code or this file here. Okay. Where is it now? Let me see. So here's my unknowns. Here's my Jacobian matrix. So I'm using the vector y to express my unknowns. So it's shown here. And this is my forces here. My system matrix is this one here. Okay. So everything there, we can look at the details a little later. But this is it. Oh no, let's see. You ready? Hold your breath. Don't. Okay, ready? Oh, wrong. This is not the right kind of model. I need to go back. This is way too complicated for us. Here. Yes. 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 It's true respect. Respect, think about this. You saw it?
Yeah.
Okay, check this later from the YouTube. So this is one of those, whenever you're going back home, you have a lot to tell your mom and dad. You can have a lot of stories about how this was this equation of motion and everything. So great stuff. So here are the coordinates when I'm solving them, but the response, you saw that. Okay, so now what I'm gonna do next is that I will put my first of all I will close these windows, and then I guess that I have to close the MATLAB too, because my computer is really making a lot of noise, which is not friendly noise. Okay, and then I'm gonna put this device back on. Okay, so it is still on. Now just a little bit of changes to my streaming. Okay, so let's not use this one, but yes, let's use this one. Okay. Here. Okay, now there's going to be an in-class quiz in a second. And then I'm going to explain the next in-class quiz in very soon to you. And then we're going to go back to Socrates and look at how the 100% success rate look like. We have a deal. Okay, my next problem is this one. So it's not just a one moving body, but two. Okay, let's raise the level of difficulty. So now we have two bodies. How is this going to be different comparing the previous example? No difference. And that's the beauty of multi-body system dynamics. We're going to simply follow again these 6 steps. We're going to follow the 6 steps and we're going to get the equation of motion automatically. Nothing we need to think, or just, it's very, very mechanical work. All right? So we're going to, first express the mass matrix, then we have to express the constraints, Jacobian matrix. That's how it goes. So there will be no surprises to you. This is just an extension to 2 bodies. If you want to extend this to 100 bodies, this will be all same again. No changes. Okay, but I have here a system that consists of 2 moving bodies. So what's going to be the number of generalized coordinates? 6. Okay, 6 generalized coordinates. What's going to be the number of degrees of freedom? 1. Because of this equation, because is 1. Okay, what's going to be the number of unknowns? Okay, so let me take a look. Okay. Okay, how we do? Okay, you guys all done with the first question? Seems that we only have 37 answers in the first question. You all done? You all enter your answer? The first question? Okay, so I can close this one and move on to the next one. Okay, close case. If you round it up, this is 100%. So 92, so it's good. It's good. Getting closer all the time. Getting closer. Is this, what about the one that will be going on next? In this example, the number of unknowns will be how many? Okay, let's put you want to take a look at this picture again. So here's a picture. So is it going to be 2, 6, 11, 14? Only one is correct. But which one is correct? Okay. And once you're done with this, then you can have a break. So can we have only 5 minutes break today? Only 5 minutes. Because very exciting stuff is coming. So what is upcoming material? So we're going to first cover this example, and then there's a recap. So summary. Okay? So you have some 5 minutes to enter your answer. Step up and stretch yourself a little bit, and then come back. No idea what's the design. Okay, you guys are back. So can we continue today? Okay. Oh, that's really clever. So some of you are looking the recording.
Sorry?
These guys are checking out how was the recording. Okay, so are we ready to continue? Okay, guys, are you ready? Okay, what is it you would like to do next? Would you like to check it out the results of the in-class quiz, or should we go to? You need to mute that because the echo. Are you guys to hear the same that I hear, or is it just inside of my head? So we all hear that, correct? Not just me. Okay, so we're gonna check the results of the in-class quiz. What if we're gonna score 100%? Party. So it's gonna be okay. So we're gonna go to cafeteria because they can. I think they have a beer in their collection. I don't know. Sounds like a kind of wild. Okay, but now we have 62 students. So and the correct answer is 11. Okay, still, if you round it up, it's 100%. Okay, so where the 11 is coming from? So where is this coming? 6 plus 5. 6 plus 5. You know, because if we go back to this one here. You know, remember what I have here. So these are the numbers you need. These are the numbers you need in order to compute the degrees of freedom. But you can use these numbers to another purpose too, to calculate the number of unknowns by this operation. Plus 6 plus 5, 11. That's how it goes. So that's the number that I'm looking here. What are these 11? Yeah, so yeah, they are generalized coordinates, 6 generalized coordinates plus reaction forces. Okay, reaction forces are the ones that are located, hold on, here and here. And then here too. So here's a 1. So there is a total of 5 reaction forces because of the 5 constraint equations. Okay, with that, I guess we're ready to move on and follow the 6 steps. We're going to follow the 6 steps to create the equation of motion. Alright, so at this time I'm not going to show off with any mathematical details, but instead I'm going to simply use pre-calculated tables. And this, by the way, is my recommendation. So if you need to compute the mass matrix for the system like this, I don't think that it makes much sense to use volume integrals. But instead, take the pre-calculated tables, and there are these engineering tables. A lot of these tables are available, and with help of these tables, you can compute how is the mass moment of inertia and other features too. But here we're mainly looking for mass moment of inertia, because in our diagonal representation, we're going to have just the mass of the bodies and then the mass moment of inertia. Now, in order to understand this first step, we have to take a look at this configuration again. You know, look where the body reference coordinate system is located in a body A. That's center of the mass. Where is located in a body B? Center of the mass. So both will result to diagonal representation of mass matrix. Okay? So how is it then? So here it is. So here's the first mass matrix associated to body A. Here's the second mass matrix associated to body B. And now we simply use this block diagonal representation. We're going to take these two matrices and we're going to add them together in a mass matrix of the entire system. So here's a mass matrix of body A. Here's a mass matrix of body B. Rest is 0. Okay. When you look at this entire system mass matrix, entire mass matrix is an all, diagonal representation. What if I would change the position of this second body reference coordinate system to be, say, here, one end of the system? Why not? I could make it happen. But in that particular scenario, these two components would not be equal to 0. And also it would affect this guy here. So those will be the changes because of that, when I'm modifying the position of the body reference coordinate system. Okay? So that's step number 1. Done. Step number 2, Jacobian matrix. Ingredients again. We need constraint equations and we need generalized coordinates. Okay? First constraint equation is associated to point O. The point O is the one that is this one here. Okay, now here we have a temptation here. We have here the global coordinate system, and this is exactly where the constraint is imposed. Origin of the global coordinate system. Okay, can we make a shortcut? Not to use this equation, but instead, jump directly to this location. No, absolutely no. Not allowed. We always have to follow this equation. That means that we have to first travel here. That's going to be with help of R. We're going to have to account the orientation of body reference coordinate system with help of rotation matrix. And then we have to come back where we started with help of vector U bar. That's the procedure we always have to follow. Okay, so that's how it is. So that's the translation. Rotation vector U bar will be minus L divided by 2, 0, because the x-axis is pointing this direction. That gives, and then this will be equal to 0, because this point here with respect to global coordinate system is in origin. Okay, so that's where I'm going to get two constraint equations. C1 and C2. Still 3 to go. 3 to go. Second one is going to be revolute joint that combines body A and body B is located in a point P. So how are we going to make it happen? So we will express the point P with help of body A and with help of body B, and we're going to put them equal. That's going to be my constraint. So here's when I do this position with respect to body A, my translation, my rotation, vector U bar. And now look at this. This time the vector U bar is going to be L divided by 2 because X is pointing this direction. Okay? Then going to redo the same, except this time I'm going to jump this body B, and then I'm going to count the translation of the body reference coordinate system of body B, orientation, and then the vector U bar. Vector U bar, X is pointing this direction, so I have to travel negative direction. It's going to be minus L divided by 2, 0. Here's going to be my 2 additional constraints. So it's going to be a 4 constraint equation as a total once I do the math. So that's how it looks. My final one is associated to point Q, and this is going to be primitive joint. Primitive joint where the motion in a global y direction in a red font is not allowed. It will be constrained. Alright, so we're going to follow again this procedure. So we're going to first go the body reference coordinate of body B. We're going to count the orientation, and then we're going to travel this point here with the help of vector U bar, and because the y motion is constrained, this one here must be equal to 0. That's going to be my 5th constraint equation. Okay, one more step before we are ready to express the Jacobian matrix. So we have to make a list of tennorized coordinates, and not listed here, but it's going to be, you know, this is, let me point it out, this is my first tennorized coordinates, my second, my third, my fourth, my fifth, my sixth. Those are tennorized coordinates. And then I'm going to simply differentiate these 5 constraint equations with respect to tennorized coordinates. Okay, I will get the matrix that consists of 1, 2, 3, 4, 5 rows because of 5 constraint equations. 6 columns because of the 6 tennorized coordinates. Very easy. Okay. Then vector of external applied forces. So now in this case I only have here, you know, gravity force that is applying. Let me write it here. So it's applying to both bodies. So it's going to be applying in the center of the mass. And because the body reference coordinate systems are located in the center of the mass, this will be somewhat straightforward. This is the position where the force is applying with respect to body A. The vector U bar will be 0, 0. It only gives this component when I look at the position. And when I differentiate that with respect to tennorized coordinates, my mapping matrix will be the one shown here. When I compute the mapping multiplied by original force, which is 0, minus mass multiplied by gravity constant, this is the force is associated to body A. Okay? Then I'm going to redo this whole thing, but this time for body B. So again, the vector U bar will be 0, 0, simplifying things quite significantly. My mapping matrix is going to be this one here. Now that when I there is actually a force here. Excuse me. So I forget that there's a point force applying to this direction, but that too is applying in the center of the body reference coordinate system. So it's the same location. So this is the associated to point force. This is the one that associated to gravity. So tennorized force is associated to body B is the one that is shown here. The final vector of tennorized forces is the one that is shown here. So it consists of 6 components because of the 6 tennorized coordinates. Rx for the first body, Ry for the first body, theta for the first body, Rx for the second body, Ry for the second body, theta for the second body. Okay. Quadratic velocity vector, that will be equal to 0 because we have a diagonal representation of the mass matrices, so no need to worry about that. Step number 5, the painful one, really the ugly one. Let's make it happen. So this is the part we have to compute. So we have again here Jacobian matrix multiplied by velocity. That is then differentiated with respect to generalized coordinates. Finally, that is multiplied by velocities. Here's my Jacobian matrix. I'm going to multiply that with velocities. This is what I'm going to get. So it's a vector that consists of 5 components, as shown here. That I will then differentiate with respect to generalized coordinates. I will get the matrix as shown here, and that will be finally multiplied by velocities, and the final solution is a vector of 5 components. System matrix, I'm not even constructing that, but I can construct that by using a MATLAB. Should we run the MATLAB example? You saw the MATLAB example again. It's going to be the one that, this crankshaft mechanism is moving left and right. But let me show that to you. Okay, so hold on. And then I need to make a little bit of changes to the streaming. Okay, so this on and this off. Okay, so it looks all right. Okay, MATLAB is starting. Okay, I'm not going to show the details. How is this file? But that's going to be all right. So these are my coordinates here. Hold on. I don't want to show that, but this one here. So these are my coordinates. So when this file will be available in a Moodle database. So with help of Moodle database, you can take a look at how is my code. It's not professional code or anything, but let's just solve the response. Okay. So let me make this smaller. That's the way that I can see how is a response. Silence, please. Hold your breath. Yes. Can you believe it? Can you even believe this? Magic. I guess that is magic. Oh yeah, it's like... Okay. Now, very good. So that's second example. Now I need to go back to this OBS and make change my settings again. Okay, so we're back here. By the way, look how awesome is the technical stuff today. Everything works like dream. So only thing that is missing is this 100% success rate. Okay. Recap. So we're ready to move on to summary. So these are the items you must know when you get into exam. So you cannot see that. Why not? Oh, because this window, there's a delay. Hold on, so what's the window that I should show you? Let me see. Here. Okay, so here's a list. So you must know each one of these items if you want to score high in the exam. If you are in a hurry and you don't like the subject matter, that's all right too, because then I will tell you what is the topic you can skip. So it will be based on the star ratings. So each one of the topics will be identified by number of stars, and if there's a lot of stars, make sure you know that particular topic. If there's, say, 2 stars, 1 star, skip it. But if you really want to score high, you must know each one of these topics, plus you must read the lecture note. So there may be a question from the lecture note, but nowhere else. You know, I want to play fair. You know, everything that I have explained here, plus the lecture note, you cover that, and you will get. And if you really know the topic, you're gonna get 5. No more. You know, not more than that. And if you're in a hurry, then just pick the few items from the list, and which ones you should pick. Those are the ones that will be rated by a high number of stars. Okay. If we're going to get started, you know, first we're going to have here description associated to kinematics. So the kinematics is this part, so there's a good part of the items. So all that is related to kinematics, and then what comes after that is the dynamics. Now, a few basic stuff that I would like you to recognize. Please understand what's the particle. And please make sure that you know that. The particle is the one that is a dot without the rotational degrees of freedom. Please understand what's the body. Please understand what's the definition of multi-body system. So it's a multiple bodies connected together via different kind of constraints, joints. Please understand what is a kinematic system, kinematic driven system. That's the system where the number of degrees of freedom is equal to 0. And please understand what's the dynamic system. So those are the basic stuff. With that, you can get started. And then a little bit of other details, you're going to do fine. Okay, would you like to see the ratings? Okay, why not? Okay, description of planar body. 4 stars. What is this? Important. You must know that. Okay, I really hope that you got an idea about this already. So if, you know, what we're going to do to describe the planar body is that we're going to use this equation. This equation that describes every single particle in the system. And you know, the body consists of infinite number of particles. That's how it goes. Okay. So what is that we have in this equation? So we have here the translation of the body reference coordinate system. We have a rotation of the body reference coordinate system, and then the vector u bar, which is a constant. So, but it, you know, scans, it takes account every single particle within the boundaries of the body. Okay? Now the interesting component is a 2x2 rotation matrix. So the rotation matrix is a mathematically orthogonal. What is that? It means that if you form the vectors from the columns of this matrix, those vectors will be perpendicular with respect to each other. In our case, because we're dealing with the 2-dimensional space, it's going to be coordinate axes that will be perpendicular with respect to each other. They will be unit in the length, which is an extra feature. So if you actually look, what is this vector here? It's going to be the representation of the body x-axis. And this one here will be a representation of body y-axis. That's what it is. Okay. So orthogonal matrix, so that's good to keep in mind. Description of spatial body, 3-dimensional body, 3 stars, medium important, medium. So quite important, but not really the most essence of this course. Exactly same concept that in the case of 2-dimensional system, except the dimensions will be different. So we're going to have here a vector that consists of 3 components, because we have 3 axes here. We have x, y, and z axis. So that's why the 3 components. Then we have here rotation matrix. Rotation matrix can be described many different ways, but we only learned the one here in this course, and that's based on Euler angles, which will be explained next. So this matrix here will be 3x3 matrix, which, you know, typically have, in our case, have 3 unknowns, which are, you know, Euler angles. Those are the unknowns. And then I have here vector u bar, and which consists of 3 components, because the body reference coordinate system has a 3 axis. Okay, 3 stars. So medium importance. Okay, Euler angles. So Euler angles, there may be something like, okay, what's the concept of Euler angles? Then you must remember that it's based on successive rotations. Successive is a key word here. So it's based on 3 successive rotations. So first there's going to be rotation, and after that the once rotated coordinate system will be rotated second times, and then twice rotated coordinate system will be rotated third time. That's the idea behind. And it's based on 3 rotations that are this one here, theta, and this one here. Psi, theta, and psi. Okay, phi, theta, and psi. Okay, so those are the 3 successive rotations. Order of rotation we have discussed here is a z, x, z. You may consider, okay, why you want to make your life miserable by using this sequence? Why not x, y, z? It could be possible, but this is the most frequently used sequence. And this, I guess because it comes from the gyro, and you can put gyro to any orientation in a space. Each one of the methods that are based on 3 rotational parameters will suffer from singularities. And the singularity could be that you cannot differentiate the rotations. Here's the possible, it's possible if the first rotation is 0 or 360 degrees. Then you cannot differentiate the first and third rotations any longer. If you wanted to look at that, please study the Kimball locking. Kimball locking may be part of the could be question. What's the Kimball locking? Do you think that's a fair question? Well, you are not in a position to complain yet. Then in later you might do that. Okay. But like this one here, I will not ask like, okay, what is this? And give me this equation, because it's in an online exam it's very hard to do something like that, and I don't think it serves the purpose. I don't expect you to memorize something by heart that much, but memorize the concept. Here's the concept: is successive rotations. Description of velocity, 2 stars. Skip it if you're in a hurry. Okay, what is it we have here? So we got it when we differentiate the position once with respect to time. So we got here translational velocity and angular velocity. This one here is a rotation matrix that is differentiated with respect to angle theta, and it will be rotated 90 degrees positive direction. That's what it is. What is its physical interpretation? But not that important topic. Quite simple though. Description of acceleration, 2 stars. Skip it if you're in a hurry. Okay, so this one is the one that consists of 3 components. So there's a translational acceleration component, normal acceleration component, and then the tangential acceleration component. Now, something like, okay, I could ask, okay, how is a Coriolis acceleration in multibody dynamics? So what's the Coriolis acceleration in multibody dynamics when we're dealing with rigid bodies? Non-existent. We don't have such kind of thing, because we are not accounting the rotation of Earth, but we are looking just at mechanics. Okay? Generalized coordinates. Okay, this is kind of hot topic, because look at this. So this is rated as 4 stars. You must understand this. And it goes back to this equation where we're describing the particles. This was the original, where we got started. Now, what are the variables in this equation? Those variables will be called as generalized coordinates. Later, we want to use these variables to express all the forces, and we also wanted to use these variables to solve the kinematics. So these variables, they are essence. Very, very important to understand. Okay, so what are the variables then? So if you have one body, planar body, it will be Rx, Ry, and angle theta, nothing else. But the U bar is not the variable, because it points the particle with respect to body reference coordinate system. That will be constant, because the body cannot deform here. It cannot deform. Clear? Okay, clear. Then, constraint equations. 4 stars. Okay, constraint equations, make sure okay, here's my advice to you. Please familiarize yourself to symbolic math software and make sure that if there's, kind of the joints we are used to deal with, which are the primitive joint, revolute, and the revolute joint, you can make the constraint equation for any kind of configuration that consists of primitive joints and revolute joints. Because there's a high possibility that I will ask something like that. Okay. Then also make sure that you can compute the number of degrees of freedom. The number of degrees of freedom will be based on the number of generalized coordinates minus number of constraint equations. Okay. So this is a mathematical representation of constraint equations. So you can put it in a vector. And in a vector you have independent constraints that are a function of generalized coordinates and possibly time. Now if the number of degrees of freedom is more than 0, 1 or more, then you have a dynamic system. And in order to solve the response of the dynamic system, you must create the equation of motion. You must solve that in a forward of time, exactly like we did earlier today. If the number of degrees of freedom is equal to 0, then all the unknowns, which are the generalized coordinates, can be solved by using constraints equations. So it's a matter of solving the nonlinear set of algebraic equations, and that's a kinematic analysis. No need to look at any forces. It's a motion analysis. And if the number of degrees of freedom is less than 0, it is our constraint system. Okay? Clear? Questions? Okay, then. Oh, this is serious. Okay, so if there's one thing only that you have a time to study, what's that? Jacobian matrix. How many stars is here? 11. Whew. So it's very, very important. Okay, now this is a little bit of trick because, if you look at back, constraint equations do 4 stars. Generalized coordinates 4 stars. But when you put them together, it's 11 stars. So, because you must understand both of the concepts in order to compute the Jacobian matrix. Okay, so you need the ingredients are constraint equation, and then the generalized coordinates, and then it's all about the partial operations. So it's a partial operations. That's it. That's how it goes. But now here's a high risk. If you answer in the exam by using just a pen and paper, which that too will be all right, there's a risk that you can make a mistake in a math. When you make a mistake in a math, here comes the problem of the online exam. Because if you make a mistake, then it's very black and white. So it's either you get it correctly and you will score the full points, or you get incorrectly, you get nothing. That is a problem of online exam. But what are you going to do? Well, there are ways to overcome that, but we don't have that ways at the moment. So make sure that you're very careful with the mathematical details. How you can be careful with the mathematical details? Well, be careful when you do the computing, or use a symbolic math tool, which means use a symbolic math tool. Okay? Then the kinematic analysis, so we go back down to 4 stars. Okay, now this is a little bit unfair. Look at everything is rated as a 4-star. Only thing that was not rated 4-star was a velocity and acceleration. Others are very important. What are you going to do? They are very important. Okay, so kinematic analysis consists of 3 steps. So first we have to compute we have to solve the position level. Position level will be iterative process. An iterative process that is, Newton-Raphson. So we are going to get the this delta Q, Newton difference. Newton difference is not the solution, but it tells us how is that we should update the generalized coordinates to get the positional level solution. That's what it is. That's extremely important to understand, that it's a iterative process. Delta Q is not the solution, but it's a direction how to update the generalized coordinates in order to reach the destination. Velocity level is simply a substitution problem, and acceleration is a substitution, a little more complicated than in a velocity level, but other than that, it's very straightforward. Okay. Generalized forces and principle of virtual work. Principle of virtual work is very difficult concept. This is rated 3 stars. If you can understand this relation, that delta R is equal than delta Q multiplied by mapping matrix, that will be great. That will be the whole deal. And why we do this? Because we wanted to map the forces from global coordinates to generalized coordinates. Why generalized coordinates? Because the generalized coordinates are the unknowns. So those are the unknowns. So can you see the storyline here? The plot is quite clear. Everything started from the kinematics. And by the way, that's exactly what the dynamics is about. So it's all about setting rules when you define the kinematics. And the rules are how is that you define different particles. Once you set your rules, then you just follow everything very mechanically. You just follow the different kind of physics laws, and that's how you're going to get the equation of motion. But the most difficult part is the kinematics, because the kinematics you can do many different ways. But once you set your mind, then you need to be consistent. You cannot change your kinematics any longer. And the kinematics tells you everything. What are the variables? What are the things you have to express the forces, and so on and so on. Okay, so this is a mapping, and with help of the mapping we can convert the forces to be expressed by using generalized coordinates. Simple like this. Probably there might be something related to this topic as well. Generalized inertial forces. I really don't know. So there could be something like, okay, something not complicated like what I have here, but details or some kind of parts related to that, like mass matrix. How is that you can define certain components in the mass matrix, concept of the mass matrix, questions like that. Okay, so this is what we looked earlier today. Then the mass matrix, this is a detail, so it's rated 3 stars. Oh, hold on. Here. And this is what we discussed earlier, that we even practiced this today. 3 stars, so this consists of 3 components. So this is a mass of the body, this is mass moment of inertia, and this is a mapping between the translation and rotation, which is equal to 0 if the body reference coordinate system is located in the center of the mass. Okay, quadratic velocity vector. There may be something like this, concept question. Okay, what is the physical interpretation of quadratic velocity vector? And then you have to understand this is a force that the body reference coordinate system, which is shown here, is experiencing when the body is rotating and the center of the mass is not located here in origin of the body reference coordinate system. Makes sense? Okay. Then augmented formulation, 5 stars. So it's important. So like questions like what are the number of unknowns? What are the unknowns? Do you think that you can answer that? Good. Because we repeated that a few times today. And then this concept of we moving from differential algebraic equation to ordinary differential equation. Quite important too. Okay, so here it is. How is this going to happen? So it's going to happen such the way that next Monday at 0:05, so right after midnight, the online exam will be available for you, and you will have 2 attempts. And the 2 attempts means that you take a look at the instructions, you read the instructions, it will be exactly the same than shown here. We will look at that in a second. And then you just click, okay, I'm ready to get started. There is a system that automatically selects your questions. And the next time you do the exam, the questions will not be the same. We have a question bank. We're using the lottery system to figure out what question goes to you. So this was the last year exam, so we have 14 questions. 14 questions, so it's quite many questions. It's XX here because the number may be different this year, depending on my speed. Because sometimes I'm kind of slow when I'm explaining stuff, sometimes I'm a little faster. And the maximum number of points is going to be 13. That's probably will be same this year. Then there will be questions that are match the following questions, multiple choices, true and false. So those are the different types of questions. You can make your selections. You can go back and modify your answers, but you can't pause the exam. Once you click it, then you will have 2 hours time to finalize it. 2 hours. Yes.
Will the multiple choice questions only have one right answer, or will there be more than one?
No comment. There's a one. Okay, I need to think about the question bank, but if I remember correctly, each one of the questions are made such that only one is correct. Now I have some good news, because if you're entering the incorrect answer, I'm going to take any points off from you. It's going to be just neutral, 0 points. But if you score it correctly, your points will get added together. And the exam time is 2 hours. And something very, very important. What we build in a system is a tracking system. And the tracking system is to sensing if there is a wrong blame. If we suspect that you're not the one that is entering the answer, but it's someone else, or you're using illegal help. Legal help is your mom and dad. You can use that. But your fellow student, not allowed. Yeah, if you use your mom and dad, you need to let us know. But other than that, it's all right. Then you can use all the material, everything, but not the fellow students. So you have to do it individually. We have the systems. I don't tell you what are the systems, but we're tracking. Okay, if we suspect that there's something wrong, wrong playing, we have the right to call you and say, okay, we want to have an oral exam with you. Every year we do that. We invited a few students to come over. We will have an oral exam. Okay, then if you kind of get an email, okay, the oral exam will be tomorrow. Make sure that you study like no limit, absolutely no limit. Because if you're unable to enter the answer correctly, we're not going to meet any longer. But you're going to meet rector. You can do pretty much whatever you want here in the university, except accuracy. This is a kind of that, I keep on telling this story and people don't trust me. Every year there's a crying and everything because for us it's a clear-cut case. We catch you, we don't communicate. We never communicate. We send this directly to rector's office, but rector will communicate. But it's not going to be pleasant communication. They will send them immediately. Let me just tell you what's going to happen. If you're an exchange student, they will send them automatically message to your home university that the student X commit this and that. What are you going to do for this? Then when you're coming back, I'm sure they're waiting for you, but not in a pleasant way. If you are a degree student here, it's very bad news for you. Do whatever you want, but don't see it that way, because the risk you do and amount you can gain, they don't match. They simply don't match. In my mind, there are just 2 crimes that get never old: murder, plagiarism. Okay. Now, what else? Okay, then this will close. The system will close on Sunday at 23:55. That's when it's going to close. you will have 2 attempts. Highest will be accounted. Highest, because I proposed that what about the average, and you did not like that idea. So the highest will be accounted. Okay. So how you, any questions? Is there now any questions or comments?
So we'll have to finish this exam from 22nd to 28th or whatever. Is it right?
No, you will have a full week. So what is the next Monday? What day is that?
Starting from 22nd, I believe.
22nd.
Is that a Monday?
Yeah.
Next Monday, 22nd.
20, yes, and then you until the Sunday.
Okay,
28. Okay, 22nd to 28. Correct. So you will have a full week time. Okay, what I recommend is that you will make your first attempt in the very beginning of the week. Do it on Monday or Tuesday, so you can see, okay, what are the questions, how they look like. And also, here's an important thing. Once you click, I'm done, you will see your score automatically. And if you score 0 out of 5, okay, then you need that, I need to redo this. But if you score 5 out of 5, that's it, you're done. If you score 3 out of 5, depending your desire, if you want to score higher than that, you need to redo it. But if you're comfortable with the 3 out of 5, which by the way is a good grade, stop it and move on to another topic. It is a good grade, because and even if you would score, sometimes the people are coming to my office and they say, I need to kill myself because I'm scoring here 4 out of 5, and this is not good. It's not making that big difference. 4 and 5 are almost same. Both are outstanding.
You mentioned about you can do exam from Monday to Sunday. There is the other course they said you cannot do exam on Sunday. I don't know if it's because of the system or because of that course. So I just want to alert my friend that maybe.
I haven't heard anything. So is there some kind of system updates, or what's the problem on Sunday?
They mentioned they cannot do exam on Sunday. So
Yeah, here you can do it.
I don't know.
Yeah, here, because it's a holiday or what? We don't have holidays here. So we're studying every day. Every single day. But yeah, so Sunday is valid. But maybe you want to do your second attempt already on Saturday. But once you're done with your attempts, that's it. And then we're going to get back. Okay, keep in mind that this is only half of the course. Another half will come right after break. And what will be available also this week will be a simulation assignment. So you can get started with that. But this is the hardest part. The next part is way more pleasant than the first part, because we're going to discuss a little further about mechanical modeling, and then soon we're going to move on to hydraulic modeling. And is, in my mind, is more pleasant topic than the mechanical modeling. It's not, the theoretically is way more simple than, concept of virtual world, concept of, this and that. So we're coming down, so it's downhill. So enjoy the ride. You can enjoy the ride once you're done with your exam. Okay, any other questions?
Other questions mostly numerical?
Okay, so let me tell you an example. There could be a system like this. I think this is a good example. So there could be a system like this. So there is a revolute joint, and the primitive joint here. And we're saying, okay, compute the Jacobian matrix. And then we're providing you 4 options with the different dimensions, different values. And you need to click the one that is correct. Multiple choices. Or I could say that true or false. True or false. And my claim is this. Multi-body system is a system where bodies are connected together via springs. True or false? True or false, by the way. So if my claim is that multi-body system is a system where the bodies are connected together via springs, spring elements. True or false? False. Or I could ask, okay, I have this system here, compute me the number of degrees of freedom. Then there will be multiple choices. Yeah. Or you need to put the number. That's true. So it's possible that we are expecting you to put the number to field, and whether there is a certain tolerance, that if your answer is within these tolerances, is considered to be correct. Okay, now my question to you is this. Do you have a can-do attitude? True. Oh, my man. Here's my man. Okay. This is it. So now there's a hour-and-a-half lecture today. So if nothing else, then I'm going to collect everything and close the streaming. And now we will not see you on Monday. Keep this in your mind too. There is no lectures next week. And then another final note is this. Right after exam week, our lectures will be on Tuesdays, no longer on Mondays. And the Tuesday, I think at the time is not same. It's sometimes in early afternoon, like 2 o'clock, I believe. And the place too, that will be different. So please consider those changes. All right, so now I will stop the streaming because today I'm very much in a hurry. So if you have any further questions or comments, you're not going to be able to discuss with me today because I need to run.